Welcome to Rationals for Pre-Calculus of Math 11. Today we're taking a look at applications of rational expressions, section 7.6, which is really just word problems. Rational equations can be used to model real-world problems, and there's really three types that we're going to take a look at. You should be able to do these without a problem. Involving motion, work, and proportions really is what we're looking at. So what I'm going to do is I'm going to go through these three. I'm going to set up a couple of techniques that you can go through, and hopefully you can apply these to kind of your own questions. This is a distance, velocity, time idea again. So we have d equals vt. Lenny is able to drive his empty truck to the Ostrich Emporium, which is 240 kilometers away, at a speed of 20 kilometers an hour faster than his fully loaded return trip. Let's take a look at the tagline here. If the total round trip takes 7 hours, then determine Lenny's speed from the Emporium. So it's his speed from that we're concerned about. So let's go again with this table. A to and from table with distance, velocity, and time. So that's to the Emporium, and that's from the Emporium. That's distance, velocity, and time. Distance is 240 kilometers both ways. We want Lenny's speed from the Emporium, so that's going to be our variable. That's x. And his speed to the Emporium is x plus 20. He can go faster because his truck is empty. So a lot of times, think of a little bit of common sense in here, and we can figure out if it's a reasonable answer. Here, time is distance divided by velocity. Very similar setup to what we had in that previous section. Sorry, that's 240 over x. So 240 over x plus 20 and 240 over x. If the total round trip takes 7 hours, so this total time was 7 hours, that's a combination of his trip there, which is 240 over x plus 20, and 240 over x. So what we have here is we have a rational equation now that we can solve. Now let's talk about maybe some restrictions. X certainly can't equal 0, x certainly can't equal negative 20. That makes sense. We're not going to stop, not be able to move or move backwards in time to get there. Lowest common denominator here is x plus 20. So if you think back, the technique we used is we would multiply both sides of the equation by x plus 20. So let's multiply that by 7. And let's also multiply the right-hand side by that common denominator. So, very similar to last class, we're going to expand this. We have 7x squared. 20 times 7 is 140x. Let me multiply or distribute this two terms. That's 240 over x plus 20. And we have x plus 20 times 240 over x. And again, we get some cancellation, which is the whole point of multiplying by the lowest common denominator. The left-hand side is 7x squared plus 140x. The right-hand side is 240x plus 240x. And 20 times 240 is 4,800. So, looks like we have a bit of a quadratic equation that we need to solve here. Let's group everything over into the left-hand side since it's positive x squared there. 140x minus 240x minus 240x is negative 340x, and we have minus 4,800, and that equals 0. You can run this through the quadratic equation. This does factor though. It factors into 7x, x, let's throw a 60 there, and a plus 80 there, and we get solutions of negative 87ths and 60. Let's check this against some restrictions. Speed of negative 87 doesn't really make sense. We want a positive speed here. So we're probably looking at velocity or speed from is 60 kilometers an hour. So 60 kilometers an hour, it might be worthwhile to plug that in to maybe the original equations and give yourself an idea if that's a reasonable answer. But I think that's pretty good. So let's take a look at work. And work is really about proportions. We're going to create another table here. It takes Lenny 6 hours to unload. So what I want to do is let's create a table of the principal players here. We got Lenny. We got Carla. And we have the two of them together. So let's see here. We got kind of a total time. For Lenny, it takes him 6 hours to do the work on his own. So by himself, it would be 6 hours, but when Carla helps, it only takes 2 hours. Well, we don't know how long does it take Carla to unload the truck. So let's take how long would it take Carla to unload. That's kind of our variable. Let's call that T maybe, because we're talking about time. For Lenny by himself, it's 6 hours. For Carla by herself, it would be T hours, and together we know that's 2 hours. So this is kind of a step where we talk about the fraction of time that they can do it in. We're talking about hours here, and we want to know what's the fraction of time per hour. So per hour, Lenny works 1/6. So every hour, he will work 1/6 of the work. Carla works 1/t. So how do we figure those out? It's really just the reciprocal. You put 1 divided by 6 or 1 divided by t. Now, since it's 2 total hours of work, what we're going to do is we're going to multiply both of those by 2. So 1/6 times 2 is 2/6. And 1/t times 2 is 2/t. And the total together is 2/6 plus 2/t, and that has to equal 1 complete amount of work. So let's take a look at this. We have the lowest common denominator, 2/6 plus 2/t equals 1. Our LCD here is 6t. Certainly the 2/6 you could reduce, but let's just leave it as that. So 6t times both of those, and it equals 6t times 1. We have some reducing. The 6's cancel here, the t's cancel here, and what I end up with is 2t plus 12 equals 6t. 6t minus 2t is 4t equals 12, and dividing by 4t equals 3. So it would take Carla 3 hours on her own. So 6 hours for Lenny to do it by himself. Carla, it takes her 3 hours. When they do the work together, 2/6 plus 2/t gives us our total amount, and for her that's 3 hours. So let's recap a little bit with work. You make a fraction of the time per minute or hour or whatever the amount of the unit of time is. So for this it was 6 hours for Lenny. So he does the work in 1/6 of the time, let's say. For Carla, since that's the variable t, she does the work in 1/t time. Those two fractions both get multiplied by the total amount of time that the project took together. In this case, 2 hours, so 2 over 6 and 2 over t. If it was 10 hours, it would be 10 over 6 and 10 over t. And we add those two together and it should equal 1 because it's 100% of the work is done as a fraction. So let's take a look finally at proportions. And proportions are really about mixing things. How much alfalfa, which is a type of grass, does Carla need to add to 22 liters of ostrich pellets to make an ostrich food that is 30% alfalfa by volume? So again, let's take a look at what we're solving for. How much alfalfa? That's the question. So let's let x equal the volume of alfalfa. It's just funny to say the word alfalfa. Then the total volume of this mix is the amount of alfalfa we added plus the 22 liters of just the straight ostrich pellets. So we have a total volume of x plus 22. We have the volume of alfalfa as being x. So what do we want? We want 30% alfalfa by volume. That means it's 30 over 100. So 30%, 30 over 100. That's pretty straightforward. And how do we figure that out? That's volume alfalfa divided by total volume. And that has to equal 31/100. So the volume of alfalfa is x over x plus 22 for the total volume. That has to equal 30 over 100. So this is actually, these mixing questions probably work out to be a little bit easier type questions. Mostly because it's just kind of a cross-multiplying idea. But let's get away with that lowest common denominator again. Multiply the left-hand side by 100, x plus 22, and it's x over x plus 22. The right-hand side, 30 over 100, and that's times x plus 22 and 100. I kind of wrote those in different order there. Let's reduce. And we have 100 times x left on the left-hand side, and 30x plus 660 on the right-hand side. Subtracting 30, we end up with 70x equaling 660. And dividing by that, we get 660 over 70, which we could reduce that and say that x is 66/7 of a liter, which is about 9.428 liters of alfalfa. So let's talk about the mixing proportion kind of volume. It doesn't need to be volume, but any kind of proportion problem. Basically, you take the percentage, which in this case was 30%, write it as a fraction, 30 over 100. And you write another fraction, another rational expression with the volume of the alfalfa, in this case, over the total volume. So alfalfa plus what we originally started with. That's a pretty common word problem, certainly for this stuff. So those are the three main types of rational kind of application problems we'll see. You got to be prepared to kind of read a word problem and build it yourself. You may not see exactly one of these, but those three should give you a pretty good basis for what we're doing. This ends the notes for applications of rational expressions, section 7.6.